So, hello, good morning, everyone. So, I'll be presenting VC3, Trustworthy Data Analytics in the Cloud using SGX, and this is joint work with Felix Schuster, Cedric Fournet, Christos Gansidis, Marcos Penado, Gloria Manar Ruiz, and Marcos Sinovic. Felix should be doing the talk, but he lost his plane. So, the problem we are addressing here with this work is that cloud computing introduces privacy risks. So if a user wants to do cloud analytics today, they prepare some data and some code, then they upload the code to the cloud, the untrusted cloud, runs the code over the data, produces some results, and the results are shipped back to the user. So what can go wrong? Well, lots of things. The cloud may leak confidential data and code. It may tamper with the code and the data. For instance, privileged cloud operators may leak the data. Intruders in the data centers may also leak the data, and we know that governments may ask for access to the data. So encrypting data on disk is obviously not enough for this because users want to perform general purpose computations on the data. Fully homomorphic encryption is great, but it's still inefficient for general purpose computation, although partial homomorphic encryption schemes have been shown to be applicable to restricted cases. So people have looked at using trusted hardware to protect these workloads from attacks from the cloud, but previous work doesn't guarantee confidentiality and integrity for all code and data, or it has a very large TCB, and previous systems don't guarantee integrity of the full distributed data analytics computations. So in VC3, we are addressing this problem for MapReduce computations. VC3 protects MapReduce computations from the untrusted cloud. It ensures confidentiality of analytics code and data, and we use trusted SGX processors and compiler-enforced invariants to achieve this. We also ensure integrity of distributed MapReduce computations, and we do this with a small software TCB and low overhead. So I'm going to give you a quick background on MapReduce and Intel SGX. Then I'll do an overview of the VC3 design. I'll explain some details about our lightweight protocols and our compiler-enforced invariants, and I'll conclude with some numbers. So MapReduce is this very popular data analytics programming model, and the idea is very simple. So the users specify inputs as a set of input splits, and they write map and reduce functions. The data analytics framework then runs the map functions in parallel over the input splits, and this can be very large data sets, think terabytes plus, and the map functions output intermediate key value pairs. The system then does a group by on the keys of the intermediate key value pairs and calls the reduce functions in reducer nodes, and the reducer nodes output results. So it's a very simple programming model, but it is very popular and it is very useful to do data analytics. The other piece of background is Intel SGX. So SGX is a set of extensions to the Intel instruction set architecture that Intel has defined. And what these instructions allow you to do is they allow a user mode process to define a region of virtual memory and say that that region of virtual memory is isolated from the rest of the system. And these regions are called enclaves. And SGX supports TPM-like features like sealing and attestation. And it also does encryption when cache lines are evicted from the CPU and are written back to RAM. Finally, SGX allows the enclaves to do fast I/O through shared memory. So the code that is running inside of these enclaves can read and write freely from the full address space, and this can be used to do fast I/O. So we are going to secure these MapReduce data analytics computations, and we are going to use SGX enclaves. So at a very high level, what we're going to do is we're going to encrypt data and code, and we're going to keep that data and code encrypted except when it is inside these SGX enclaves. And when it is inside the enclaves and inside the CPU, the data will be in plain text and the code will be in plain text, and it can run efficiently inside the CPU. Is this it? Are we done? No. There are lots of challenges that we need to address here to make a practical system that works for data analytics computations. One of the challenges is how to partition the system to achieve a small TCB. What is exactly this code that we trust to get access to the data? We would like to keep that as small as possible. The other challenge is to guarantee integrity of the whole distributed computation. These CPUs protect these regions inside a single machine, but to build a full distributed system, we are going to be using many machines. And at some point, data needs to come out of these regions, and it is handed over to the operating system. The operating system can do then many bad things. It can corrupt the data, duplicate it, drop it, and if we don't do anything, we wouldn't be able to guarantee integrity of the full computation. The final challenge that we need to address is that the code that is running inside of these regions may have unsafe memory accesses. And we would like to prevent leaks due to these unsafe memory accesses. And finally, I will just add as a bonus, we would like to integrate our design with existing cloud frameworks so that we can easily deploy this on existing data analytics frameworks. Okay, so the first challenge is to partition the system to minimize the TCB. So what we did there was we defined a simple programming model, the traditional MapReduce programming model, and users write code in C++. They write map and reduce functions. We link that user data analytics code with a small library that includes, in our prototype, mathematical and string functions. So these would be typically, data analytics libraries. And we encrypt this secret code, and we bind it to a small amount of public code that implements our public protocols. And we put all of this in a DLL where the secret code is encrypted. So this is going to be the code that we're going to trust and give access to the data. And overall, we're talking about a few thousand lines of code. So it's a very small amount of trusted code. Outside, so this code then has a very narrow interface with the rest of the system. The code just reads and writes key value pairs from the rest of the data analytics system. And outside the trusted boundary, the code that runs in the untrusted area does things like creating these SGX enclaves, talking with the operating system, binding to unmodified Hadoop installations. But all of that code, which is, if you include the operating system and the hypervisor, is a lot of code, but all of that code is untrusted. So what we achieve here with this design is that the TCB is essentially the code that we put inside of this DLL, the secret data analytics code that the user writes, and the hardware TCB is the SGX processor. So the software TCB is 3 orders of magnitude smaller than the operating system, hypervisor, and Hadoop. So we have this very small TCB. So this is how we package the code to do the data analytics computations. Then we ship it to the cloud. We then run a key exchange and remote attestation protocol to share secret keys with the code. I'll refer you to the paper for details on that. And once the key exchange protocol completes, the code is ready to run, and we can run the data analytics job. So our job execution protocol is going to do the normal sort of data processing that you'd expect from a MapReduce job, but it's going to do a few additional things. So the compute nodes are going to output some secure summaries of the work they did. And these secure summaries are going to be aggregated conceptually at a verifier node. And the verifier node is going to check the consistency of all of these summaries and detect any tampering with the computation. And both the key exchange protocol and the job execution protocol integrate with unmodified Hadoop. We can run this on unmodified Hadoop installations, and the protocols tolerate failing nodes, straggling nodes, the usual things that you expect from these data analytics frameworks. So let me give you a little bit of more details on the job execution protocol. So during a normal data analytics computation, the mappers will be producing these intermediate key value pairs to send to the reducers. So we change this, and we have a different format for these intermediate key value pairs. So we're going to put the original key value pair, encode it inside a new key value pair, and we encrypt that with the AES GCM. And for the key, we're going to replace the key with a pseudo-random function over the original key. And in the value, we have some extra information like a job identifier, an identifier for the mapper, a sequence number to allow reducers to detect duplicates. So this still allows the system to do the aggregation on the intermediate keys. So that proceeds as usual, but the user also writes, the tools that the user uses write a job specification that includes the set of input splits that the job is supposed to process and the code that is supposed to process those input splits. This is sent logically to this verifier node, and the mappers also send to the verifier node information such as what input splits were processed by each mapper, how many intermediate key value pairs were sent from each mapper to each reducer. Likewise, the reducers send summaries to the verifier, including what was the set of mappers they received information from, how many key value pairs they received from each mapper, for instance. This allows the verifier then to answer these questions. Did mappers process all the input data? Was any input data duplicated or dropped? Do the reducers agree on the set of mappers that processed the data? Did the reducers process all the intermediate key value pairs that the mapper sent? And if the verifier can answer positively to all of these questions, then it can certify the output of the computation. And in the paper, we also show that the verifier can be modeled as a normal MapReduce job and can be run on the normal MapReduce framework. I'll note here that our encoding of the intermediate key value, the intermediate key leaks some information about the distribution of keys. And we don't address this in this paper, but in follow-on work, we have addressed this problem. So the other challenge that I wanted to address here is that this data analytics code that the users write in C++ may have low-level coding defects. And so if you have a defect like a write through an uninitialized pointer, you can easily corrupt memory or simply leak data by writing outside of the enclaves. And likewise, if you read through an uninitialized pointer, you may be reading unauthenticated data supplied by an attacker in the cloud. So to deal with these problems, we allow, so to deal with these problems, we allow users to optionally use a compiler that enforces two security invariants. So if users are worried about these problems, they compile the code automatically with our compiler, and they get these security guarantees. One of the guarantees is what we call region write integrity, which guarantees that writes through pointers can only go to address taken variables inside the enclave or heap allocations in the enclave. And so this, for instance, guarantees that any write through a pointer can never corrupt non-address taken data inside the enclave and can never write data outside of the enclave. So that's the first invariant. And the second one is augmenting region write integrity with the guarantee that reads cannot go outside the enclave. So users can choose not to use any of these or either one of them. And just to give you an idea of how we enforce them, to check the region write integrity property, we keep a bitmap that maps every 8 bytes of enclave memory to 1 bit in the bitmap. So when 1 means the memory slot is writable. So this is a compact representation of the memory protections inside of the enclave. So if the compiler cannot check that the write is safe, it's going to check the bit in the bitmap to see if it's 1. And we update the bitmap on heap allocations and stack allocations and deallocations. We also check control flow transitions to make sure that the read checks and the write checks cannot be bypassed, and we use a similar bitmap to check control flow transitions. So that is a form of coarse control flow integrity that we enforce. And finally, the read checks are a simple range check that we enforce with a simple bit mask. And I'm not going to go into details here, but in the paper we show how we have efficient code sequences to implement the checks. To evaluate this, we implemented VC3 for Windows Server 2012, where we tested the implementation on an emulator provided by Intel. But because that emulator is not performance accurate, we measured the properties of the system using our own emulator. And we implemented the region self-integrity properties as a modification to the Microsoft C++ compiler. We tested seven applications, a mix of I/O-intensive and compute-intensive applications. And we ran experiments on a Hadoop cluster with 8 workstations. So the graph here on the slide shows the numbers, the runtime numbers for all of the applications, and the runtimes are normalized to the case where the application runs on Hadoop but is not protected by our mechanisms. So what we see there is that for VC3 we see over the base properties of VC3 we see overheads below 1%. For VC3 with the write integrity checks we see overheads of on average 4.5%, and with read-write integrity of an average of 8%. Now, when we run this on Hadoop, there are lots of things that are happening in the system that mask the real overheads of VC3. And these things are scheduling Hadoop jobs, shuffling data around, launching processes, those types of things. So to have a better understanding of the overhead, we also ran the map and reduce tasks in isolation without Hadoop. So on a single machine, just executing, for instance, a map function over an input split. And there we see some higher overheads. So for VC3, we see an average of 4%. For VC3 with region-write integrity, an average of 15%, and with the read-write integrity, an average of about 25%. So I'll conclude here and say that VC3 protects MapReduce data analytics computations from the untrusted cloud. We ensure confidentiality of code and data for these applications, and we ensure integrity of the full distributed computations. And our experimental results show good performance. So thank you, and I'll take questions.
Thanks a lot, Manuel. Any questions?
Ruby Lee, Princeton University. It's very interesting. I was wondering, when you talk about the TCB, and given that the cloud can migrate virtual machines, and there's a lot of SSL maybe involved in talking to different nodes, wouldn't the whole cloud scheduler and network stack protocol and so forth, wouldn't that have to be in the TCB?
So no. So we do rely on all of these components to run the full system. So if the cloud can, for instance, do denial of service attacks on our system by, for instance, not migrating or scheduling jobs, but those components, they can never they never have access to the plain text data that we are processing, and so they can never read or tamper with the data without being detected. And then our integrity protocol, which is based on having the nodes that have access to the data producing some summary information of what they did, what data they processed, for instance. Those our integrity protocol then aggregates all of that information and verifies that, for instance, the scheduler did not tamper with the computation. The scheduler might, for instance, try, a typical attack would be the scheduler might, for instance, not schedule a map function on a particular input split. But we would always detect that.
So might it be clearer to say your threat model doesn't defend against availability attacks, but it's fail-safe for confidentiality.
That's exactly right.
But then there's another problem. If I kind of understood your restrictions, you can't write from the enclave outside with your write restriction or something. So then how do you release the encrypted code from your enclave to the outside if you can't write or read, you know, get the encrypted code into the enclave?
So the data if you use our compiler extensions, the data analytics code cannot write outside, even by mistake. That's our sort of our threat model there. That code is not malicious, but it may have bugs. So you are right. That code cannot. But our implementation of the protocols. So I had this slide with the sort of the data analytics code and a small amount of crypto protocols. So our implementation of the crypto protocols implements the communication primitives, and that code can write the messages out. But that code first, when writing out, first encrypts, and when reading data, checks the authentication codes on the data that is coming in from the outside.
Thanks a lot, Manuel.